Repurposed graphics cards provided the massive parallel processing power necessary to turn theoretical neural networks into the modern AI boom. A standard central processing unit, or CPU, handles tasks one at a time with a few high-precision cores. While powerful, this sequential design cannot keep up with the millions of simultaneous operations required by deep learning. Graphics processing units, or GPUs, solve this by utilizing thousands of shader cores. Originally designed to calculate the color and brightness of every pixel on a screen independently, these cores enable a method of computing known as parallel processing. This schematic illustrates the difference. While the CPU functions like 4 heavy-duty transport lanes, the GPU acts as a massive assembly line. The same architecture that renders video game graphics is perfectly suited for the simultaneous matrix calculations used in AI. NVIDIA further specialized this hardware by introducing tensor cores. A tensor core is a dedicated circuit designed to accelerate the specific matrix math used in neural network training and inference. This inherent architectural advantage shifted GPUs from gaming accessories to the mandatory infrastructure of the AI era. Today, the massive demand for AI computation has produced a dense and confusing list of NVIDIA GPU models. Successful deployment depends on matching the physical silicon to your specific hardware environment. The financial stakes are high. Buying the wrong GPU segment often results in hardware that physically cannot fit into your motherboard or lacks the specialized cooling systems found in professional servers. We can evaluate the entire ecosystem by looking at 4 distinct market segments: consumer, workstation, data center, and edge. Navigating this matrix is the only way to avoid expensive hardware incompatibilities when building an AI workstation. The consumer segment includes the GeForce RTX line, targeting hobbyists and local learners. These cards utilize a traditional PC form factor that fits into most standard desktop cases. These cards deliver high matrix math performance for a relatively low financial investment, making them the starting point for most individual developers. However, consumer cards have limited VRAM. VRAM, or Video Random Access Memory, is the onboard high-speed storage used to hold a neural network's data during processing. Without enough VRAM, you cannot load large, complex models. This limitation leads researchers to the workstation segment. These cards are engineered for local high-performance research where memory capacity is the priority. As this chart shows, workstation cards look like desktop GPUs, but provide extreme VRAM capacity and higher system stability for a much higher price. While consumer cards offer the best compute per dollar, serious research on a local machine eventually requires the memory overhead of a workstation GPU. Beyond the desktop, we find the data center segment. This hardware is built exclusively for enterprise cloud architects training massive foundational models. These GPUs have no video outputs and no internal fans. They rely on external server room cooling systems and require specialized sockets that are incompatible with home PCs. This design allows thousands of units to be connected via NVLink. NVLink is a high-bandwidth interconnect that allows GPUs to share data at much higher speeds than a standard motherboard connection. This high-speed connection allows an entire rack of servers to coordinate and function as one single massive GPU. NVIDIA packages this power into DGX systems. These are fully integrated supercomputers where 8 powerful GPUs work together to handle the world's largest natural language processing tasks. The data center segment trades all consumer compatibility for the ability to scale training power across thousands of linked processors. The final segment is edge computing, specifically the Jetson line. This hardware is built for robotics and mobile hardware developers. In these environments, the primary design goals are a small physical footprint and minimal electrical power consumption. Because they are optimized for mobility, edge GPUs lack the massive processing power required to train new neural networks from scratch. Instead, they excel at inference, the process of applying a pre-trained AI model to new data in the real world. This is what allows a self-driving car to identify a pedestrian in milliseconds. Ultimately, edge GPUs sacrifice training capacity to make AI mobile, durable, and functional outside of a data center. After choosing a segment, the actual performance of the card is defined by its architecture, the specific generational design of the chip's internal components. This timeline identifies the legacy naming system. Letters in models like A100 or V100 designate the architecture, P for Pascal, V for Volta, and A for Ampere. But recent generations like Ada Lovelace have dropped these letter designations. Newer architectures provide dedicated hardware, like the Transformer Engine. The Transformer Engine is a specialized hardware and software layer that automatically manages data precision to speed up generative AI models. The Blackwell architecture advances this further by using FP4 and FP6 data formats. FP4 and FP6 are 4-bit and 6-bit floating point formats that represent numbers using less memory, significantly increasing processing speed for large language models. Identifying the architecture generation is the only way to verify a card's actual technological capabilities before you buy. The golden rule of AI hardware is simple. Your environment dictates the segment, while your budget dictates the architecture generation. For the budget-conscious hobbyist on a home PC, the consumer GeForce RTX segment is standard. For researchers needing massive memory in a desktop, Workstation RTX provides the overhead. And for enterprise architects scaling models, the data center segment is required. Always watch for naming traps. The cutting-edge RTX 6000 uses the Ada Lovelace architecture, but the older Quadro RTX 6000 uses the Turing architecture from several years ago. They are not the same card. Do not rely on marketing buzzwords. Confirm the architecture generation on the spec sheet before you authorize a purchase. Aligning your specific workload with the correct segment and architecture converts raw silicon into a functional and efficient AI ecosystem.